Alrighty, so let's take a look at a discrete random variable combination, and we're going to look at this question from the 2013 exam, and we have a few other questions as well. So let x represent the number on the face that lands up with a fair six-sided number cube that is tossed, fancy word for one single dice, a die. Now the expected value of x is 3.5, and the standard deviation of x is approximately 1.708. Two fair six-sided number cubes will be tossed, and the numbers appearing on the faces that land up will be added. Which of the following values is closest to the standard deviation of the resulting sum? So there's two cubes that I'm tossing, and we're going to call this y, which is the resulting sum. And I'm going to do x plus x. And you might wonder, wait, Mr. Pinto, isn't this the same as 2x? And you wouldn't be entirely wrong. But here's the difference between the left-hand side and the right-hand side. So on the left-hand side here, I am saying that I'm taking two separate objects, two separate distributions, and I'm adding them together. Whereas the right-hand side says I'm taking one dice, doing it that way, and then multiplying those results by 2. These are not, what is it, you and I? We are not the same. So we have x plus x. I'm taking two separate things, putting them together, whereas 2x means I'm taking one thing and expanding it. So we need to be very careful with the phrasing of the problem. Usually sum or difference will indicate that it's a combination, whereas if a function is given to you, typically that it's indicative of a transformation. So if y equals x plus x, and I want the standard deviation of y, I want this. This is my term. So my formula would be sigma x plus sigma x squared, the Pythagorean theorem. Okay, so let's figure this out. So sigma y will equal 1.708 squared plus 1.708 squared. Okay, so sigma y will equal that resulting sum combination of approximately 2.415, which we can see is right here. Now, on the inside, and I wouldn't get into this practice, but if you see it mathematically, there's nothing wrong there. The inside is equivalent to 2 sigma x squared. And if you don't see it, don't freak out. Here's one, add them together, you get 2. Don't get into the practice, just keep it as normal. Keep it in a way that makes sense to you. No need to get spicy. It's multiple choice, so it's either right or it's wrong. No one's going to see your notation. So just do the steps that I am telling you to do. All right, so what is the mean of the resulting sum? So let's look here together. So if I want mu y, I'm actually going to add mu x plus mu x. And so that would be 3.5 plus 3.5. So my resulting sum would be, well, you guessed it, 7 units. What is the mean of the resulting difference? Okay, so if y is their sum, let's call z the difference. X minus x is 0x. Okay, well, let's see here. Mu z will equal mu x minus mu x. And we know that anything minus itself is going to give us 0. Okay, what is the variance of the resulting sum? Now this is where it gets kind of fun. So now we're back to y. So this was y equals x plus x. So now variance is the square. Well, we can add variances. We just can't add standard deviations. So let's compare these formulas here. Notice here, sigma y squared, the variance of y, equals the variance of x plus the variance of x. Well, okay, look how similar this is to the original equation that I used. The only difference is that instead of this being squared, this is square rooted, because here I want the standard deviation, whereas here I want the variance. So lucky for us, we can actually just add the variances. So let's find those variances. That's going to be 1.708 squared plus 1.708 squared. So the variance of y is going to give me the equivalent of about 5.835. This is the variance of y. And if I wanted the standard deviation, guess what? If I took the square root of 5.835, I would get 2.415, our standard deviation of the sum. So that's how they're connected. The variance is the standard deviation squared, and the standard deviation is the square root of the variance. They're inverse functions, inverse relations of one another. Okay, now here's where it gets spicy now, and this is why I need you to always, always, always define what you're doing. What is the mean of the resulting sum of rolling 3 dice, 3 die? So let's take t for the total, And I'm going to roll the first die, I'm going to roll the second one and the third one. So if I want the total mean, I'm just going to add them all 3 times. And again, Mr. Pinto, isn't this the same as 3x? Well, think about this. This is saying I'm taking 3 separate die and I'm putting them together, whereas 3x is saying I'm taking 1 die and I'm multiplying those results by 3. Mathematically, they might be the same, but in practice, they are not the same. So we're just going to take this mean here and we're going to add it 3 times. And when I do so, I'm going to get that mu t is going to equal 10.5. Now, if we want the standard deviation, well, lucky for us, we're just going to add the variances 3 times and then take the square roots. And again, you don't have to do this, but if you see it in your head, this is the same as 3 sigma x squared. So let's take the variance here, and sorry, I'm kind of writing all over the place. I get so excited about combining these things. So that plus this is going to give me a variance. No, it's not a variance, sorry, because I'm square rooting. Sigma t is going to be about 2.96. So this would be the resulting parameters of a distribution if we were to roll 3 independent randomized, completely fair die. Yeah, I always get confused on that. But that's just an example in the discrete sense. So what I need for you all to do now is try it out for yourself. So reference these if you need, and go ahead and reference our formulas here. These are also on one of the first few pages in your notes. But you can see if you're adding or subtracting, you're just doing that to the means. And notice that the spreads, doesn't matter if you're adding or subtracting. When we combine, we're putting 2 unknowns together. Therefore, there's going to be more variation in the distribution. And then here we have the specialty cases, which we'll do an in-class example of this. But for now, I need you all to practice the following problems. So go ahead and pause the video and try out this example here from AP Classroom, as well as this FRQ from 2002. Pause the video, give yourself, I'd say maybe about 10-ish minutes. Best of luck, and then we'll come back together and we'll review our work. Okay, so here we have another discrete random variable t, which is defined as r minus s. They are both independent, and now I just use my formulas. To find the difference of the means, I take the difference of their means. 10 minus 7 gives me mu t is 3. And then again, I'm combining 2 distributions, so I'm going to have more variability in it. So to find the standard deviation, we use the Pythagorean theorem of statistics, and we get that the sigma of t is approximately 5. So these numbers work out. They're not always going to work out nicely, as we saw in the previous example, but all bueno, just verify with your calculator, and there'll be multiple choice questions. So you'll be able to see where you went right or where you went wrong. And then lastly, we look here at this FRQ from 2002, and it shows up every so often that you're doing a combined normal distribution question. So I see I have 4 runners on a team. And so the distribution is approximately normal. What are the mean and the standard deviation of this distribution? So the total time would be t equals runner 1 plus runner 2 plus runner 3 plus runner 4. So t is going to be distributed normally. We add all the means together to get 18.9. And we use the Pythagorean theorem of statistics to get the standard deviation of about 0.3003. So that would be our distribution. And then if we want the probability that the team will beat its own record, well, statistically speaking, that means that our total time will be less than 18.4 minutes. So we would do some z-score stuff, draw a picture, use our probability statement, but our final answer would come out to about 0.0475. Well, now you know a little bit more about combining discrete random variables and continuous random variables. We've transformed random variables, and we've also defined the parameters of the random variables. And now we're actually going to get into 2 special types of discrete random variables for the rest of this unit. We're going to talk about the binomial distribution and the geometric distribution. So stay tuned to learn a little bit more about these special types of discrete random variables.